All right, we've got 22 participants right now. So I think that we're all mostly here. So let's get started with our second LAMMPS session now. So let me just begin by asking real quick, how many of you guys have had a chance to work the exercises that I gave 2 days ago? So put in the chat if you've done it or if you haven't done it. I'd be interested in knowing, your experience going through that. Anybody? Okay. All right. So maybe let's take just a moment to address some of the questions that came up there. Thankfully, the stuff that we're going to be working on today is going to be largely sort of independent of the stuff that was in the exercises. So you'll still be able to proceed with today's tutorial, even if you had difficulty with the exercises. But if you could just tell me very briefly, what did you find to be the most challenging? And you can type it into chat, but you can also unmute yourself and just say it. There's not too many of us.
Participants are currently set up to not be able to unmute themselves, but if they raise their hand, we can unmute them.
I see.
So reminder that we are recording this session.
Gotcha. All right. So whatever you prefer, if you want to write it into here we go, Nadia. Ask to unmute.
Hi. So I had trouble first in MATLAB building a not cubic lattice. So like I wanted to do the BCC iron because I think I'm going to be using that for my actual project. But I had trouble like coming up with because it's a more complex geometry. And then I also had trouble when I was going into the terminal and uploading my my text file with all the coordinates, and then I wanted to like see what atomi would give me. But then for some reason when I guess I don't know, I'm trying to troubleshoot that right now. Like when I went back into the terminal, the intro lamps folder wasn't there anymore. So like I unzipped it and then I uploaded my text file, but when I go into to the folder where it is and I type in like ls, it's not there. And I'm not really sure how to fix that because when I go to like my file explorer, I see it there, but then it's not. So I don't know. It seems like kind of more of a personal problem. I wish like someone could like sit down with me and be like, "What's going on?" But I think some other people also had trouble like building a different type of lattice in MATLAB.
Okay. Well, let's address some of those things. Let me see. Who else can anybody else mention what issues they were having? Were they similar issues or something else? So let's see. Abika says, I didn't have trouble with the terminal, but I was coding for the non-cubic structure. I contacted Peng about it earlier. He said he'd go over with me in a Zoom session. Okay, so, all right. And there were a couple of other people who had issues, problems as well. So anybody else want to chime in before I sort of, go off on this? Cubic. So, all right, so no, I mean, I'm not hearing anybody else saying anything. So what I'm going to do here is I'm just going to very quickly talk about this issue of setting up the cubic lattice or the BCC lattice. This way, you guys will still have your FCC lattice to work on. So not all will be lost. You'll still be able to work on that. But I'll show you at least, more or less how it's done. So let's just do that real quick. So what I'm going to do here is I'm actually just going to use my my desktop. I'm not gonna do this in the virtual terminal because I think it's going to be a little bit faster this way. So I'm just going to use the MATLAB on my desktop. So here's MATLAB on my desktop. Hopefully you can all see it. And let me enlarge this a little bit. So I'm going to write myself a new script. Of course, I don't have to do this in a script, but I like to do it in scripts because when you do it in a script, all the commands are saved. You can go back and edit them later if you need to, so you're not having to retype things into the command prompt all the time. So I'm going to write myself a little script. I opened it in a directory which is the same as the tutorial, so I don't get it lost. Let me just, for those of you who haven't seen this before, in MATLAB, if you want to make a comment in your script, you can use this % sign. So I'm just going to say making a BCC structure. Okay. And just like I did with simple cubic, what I'm going to do is I'm going to specify how many unit cells on the side I'm going to have. And I can't remember now if the exercise asks for a specific number, but I can put whatever I want right now. I'm just going to put 5. I can always change that later to 10 or 15 or whatever I want. I can change that later. Okay. So I'm going to set it equal to 5. Now, let me just pull up real quick here, BCC crystal. Okay. Some people are, you know, will discourage you from using Wikipedia or something like that. I never do. I think Wikipedia is awesome. If you want to do anything about, you know, basic stuff like crystal structures or basic math or anything, I think Wikipedia is great. Great resource. I support it. These are sort of the most common cubic crystal structures. And last time we talked about this primitive cubic or simple cubic, as some people call it, crystal structure, the simplest kind, right? Body-centered cubic, BCC, or face-centered cubic, FCC, they're both cubic, right? So they're not non-cubic, they are cubic. The only difference is that the cubic unit cell, which is the repeating motif, the thing that repeats, does not have just one atom, it has more than one atom, right? So the cube in the simple cubic case has just one atom on the corner, that's it. In the case of a body-centered cubic material, each cubic unit cell has not one but 2 atoms, right? There's an atom at the corner and then there's an atom at the center, okay? Let me just pause for a second. When you look at this picture, you know, you see that every corner has an atom and then the center has an atom. How come I'm saying there's only one atom at the corner? Anybody? Does anybody want to tell me how come we have just one atom at the corner? You can put it into the chat. Where's my chat? Anybody want to say it? Why am I saying that there are only 2 atoms? Right, exactly, because each one of those corner atoms, you know, you can think of it as like the corner slices off an 1/8 of an atom. Another way to say it is this motif, this cubic unit cell repeats. You know, so you're all familiar with laying tiles on a bathroom floor. That's like a 2-dimensional tiling. A crystal is like a tiled floor in 3 dimensions, right? So the tiles go in 3 dimensions rather than in 2 dimensions. So basically, if you have an atom at one corner, atom in the center, and you just repeat that cubic unit cell, you stack it like a bunch of bricks, you're going to get atoms overlapping each other, those atoms repeating. Okay, I don't know why I've got this thing going, so just 1 second. Okay, so the big difference between simple cubic and BCC is that BCC's got 2 atoms, simple cubic has 1 atom. How many atoms does face-centered cubic have in a cube? Anybody? Take a guess. 4, that's right. Because there's the atom at the corner, and we've already agreed that, you know, there are 8 corners, but each corner contributes 1/8. And then there are 6 faces, and each face contributes 1/2, right? So overall, you've got 4. This is important because it's going to tell you basically how to build this thing later, all right? So let me go back to MATLAB, all right? And the first thing that I'm going to do is I'm going to initialize my my variables. So basically, I'm going to, you know, initialize a vector of position variables. You remember that last time I said it was going to be x equals 0s, and then I put in n cubed 1. So this is basically, the 1 here means that I have just 1 column. So this is a vector, okay, with n cubed rows in one column, right? Now n cubed is is the number of unit cells, right? So if I have 5 by 5 by 5 unit cells, then I have a total of 125 unit cells when I tile them in 3D. And if I'm working with a simple cubic crystal structure and in which every unit cell has just one atom, then n cubed is also the number of atoms. But if I'm working with a BCC structure where each cube has 2 atoms, then the number of atoms that I'm going to be putting in there is going to be 2 times the number of unit cells. Okay, so far that's the only difference from what we did yesterday. Okay, and of course I'm going to have just as many y coordinates as I'm going to have x coordinates. So I'm going to, and same thing goes for z coordinates. So I'm just going to initialize those to be the same. All right, everybody with me so far? Later, I was going to do some for loops, and in those for loops, I was going to have a counter. So I'm going to initialize that counter, and I'm going to do the for loop from I equals 1 to n, for j equals 1 to n, for k equals 1 to n. And then I'm just going to close them out. Okay, and then inside these for loops, I'm going to be incrementing this counter, right? So far, I'm doing everything exactly the same as I did before, right? You see that? All right, everybody with me so far? So far, so good? Okay, so here's the only difference. When I was doing the simple cubic case, what I did is I said x ct is equal to I divided by n, okay? And then I, had these other things for the y's and the z's as well. So here's z and here's y. For y, I use j. For z, I use k. Okay, right? That's the atom that's sitting at the corner of the unit cube, of the repeating cube. Okay. Now, since this is a body-centered cubic structure, it has 2 atoms per cube. I'm just going to copy this and do it one more time. Okay. And the only thing is that I'm going to displace these coordinates so that they're not sitting at the corner, but at the center of the cube. Okay, so plus 1 divided by 2 times n. That's the little, actually, let me do it differently. I'm going to say, just so that I'm going to say displacement equals 1 divided by 2 times n. Okay, and each one of these atoms here is going to be displaced by that little increment. Okay, so basically all I'm doing here is I'm putting, oops, I didn't save it yet, but I'll save it in a minute. This is the atom that's sitting at the corner of the unit cell, okay? And this is the second atom, okay, which is sitting at the center of the unit cell. And what I've done here is I've put that atom at the same location as the corner atom, and then I've displaced it by half a unit cell. Okay, that's it. That's all I need. Does everybody see why I did 1 over 2 times n? Why did I call the displacement 1 over 2 times n? Anybody? Hey guys, better to ask me than to suffer in silence. If this is something that is unclear. Nobody? Everybody gets it? Yeah. So right. So we're putting all of these atoms into a unit cube, right? And so if I scale, if I have a unit cube and I know that that unit cube has to be divided into 5 lattice parameters, or more generally speaking, n, capital N lattice parameters, then I know that the width of one of those cubic unit cells is going to be 1 over n, right? 1 over n is the width of the unit cube is the width of the cubic unit cell of the crystal when I cram n unit cubes in the length of when I cram n of those unit cells into a unit cube. I hope that I'm not like confusing you guys too much by this, but basically I have this interval from 0 to 1, and I have to put in n cubes into that, so the length of those unit cubes is 1 over n. Okay, and then half of 1 over n is just 1 over 2n. Right, so that's just half the length of a unit cube. So hopefully that's clear. All right, So I think this is all I got to do. And then, of course, at the end, I have to output it. So I usually use DLM write. I'm going to do M. And last time I found that I needed to put in new delimiters. So do that. And I'll call this bccstr.txt. Okay, that's how we'll do it. Anything else here? You have to define M, right? So M is going to be, first it's going to be, I think last time I defined for myself a vector of ones. So 1, 2 times n cubed. Okay, so A times, anybody know off the top of their head what the atomic mass of iron is? No? So iron atomic mass 55.9. Okay, that's what Google tells me. All right, iron atomic mass 55.9. Okay. I think next was going to be the atom type, and I can't write strings with DLM write, so I'm just going to use pi as I did before. Then I'm going to have x, y, and z. And finally, I'm going to have a times 0, a times 0, and a times 0. Was there, I can't remember now, were there 2 of those, or just, were there 3 or just 2? I'm just going to see if I can open this. Where's my text edit? Where's text edit? There it is. Okay, let's see. 1, 2, 3, 1, 2, 3. Okay, so 3. I think I got it. And I have to close this. And now I have to save this. So let's call it FE crystal. Save. There it is. All right, FE crystal. All right, here is my FE BCC structure. All right, let's open this with text edit. That looks good. That looks about right. And actually, now I can show you what I was going to do with this pi thing here before, because I think text editor will let me do it. So I should be able to find and replace. I'm going to find this and replace it with iron. Okay. You see what I did? Voila. So now I've taken this whole thing, I've replaced it with iron. Let me just take one of these structure files that I had here. I mentioned that we can just copy and paste the header. That's what I'm going to do again here. Copy and paste the header. So copy, paste. All right. I have to change the number of atoms. How many atoms do I have in this crystal structure? Anybody? 250. Okay, great. And I have to resize rescale the size of this model. So anybody know off the top of their head what the lattice parameter of alpha iron is? What is the lattice parameter of BCC iron? .87, great. So, and we said that we were going to put 5 of these unit cubes of these, sorry, not unit cubes, but 5 of these cubic unit cells next to each other. So the complete dimensions of the model are 5 times the lattice parameter. So what's 5 times 2.87? 14.35. Okay, so we're going to put in 14.35. 14.35, 14.35. And I believe we're done. I think. Yeah, looks like we're done. I am going to load this up to my virtual terminal so that I can view it using Atomine. Do we have to do the find and replace thing? No, you do not have to do the find and replace thing. You can just name your atoms pi. You can name them 3.14159. It's fine. It's the only thing is that, and I'll show you this in a minute, when you open up a structure using Atomi, you can click on the atoms, and Atomi will tell you the name of that atom. And if your file names that atom 3.14159, then that's what Atomi will tell you. However, if your file names that atom iron, then Atomi will tell you iron, right? So it's a little bit, you know, you basically you get what you put in, right? What you put in is what you get. But I mean, the find and replace thing is just an easy way. You know, I put in pi because it's a unique number, and none of the coordinates are going to have the number pi as the coordinate. So if I do replace all pi with iron, I know that I'm just going to end up, you know, renaming all the atoms to iron. So it's just a simple workaround. It's just a simple trick, editing trick that I use. Of course, it is entirely possible. It is not too hard and relatively easy to write yourself a MATLAB script that will simply write iron, right? So it's not that difficult to, you know, have MATLAB write out a character instead of just a number, right? It's not hard, but I don't want this tutorial to become a MATLAB tutorial, so I just tried to keep it simple. What was the value 2.87? So 2.87 was the lattice parameter of iron expressed in angstroms, right? Remember that we're using angstroms here to, you know, as our unit of length, right? An angstrom is a meter divided by 10 to the 10, right? So 10 to the minus 10 meter is an angstrom. So an angstrom is 1/10 of a nanometer. It's a short distance. The reason why people often use angstroms when they talk about atomic structures is because you may remember from your chemistry, the length of a hydrogen bond, an H2 bond, is about an angstrom. It's actually, I think, slightly larger than an angstrom, but it's about an angstrom. And in most transition metal crystals, like if you were to take iron or gold or silver, you know, copper, whatever, most of those crystals have an interatomic distance, right? The spacing between atoms is about 2.5 angstroms. So an angstrom is kind of the natural unit, you know, scale unit to use for measuring lengths. So 2.87, that's basically saying when you look at that unit cube of the iron crystal structure, the BCC crystal structure, you remember that unit cube that I was showing you just a moment ago? So BCC crystal, right? When I went to Wikipedia, I was showing you this guy. That's the BCC crystal. This A, the A that you see here, is the lattice parameter. That's basically the length of one of the edges of this unit cube that's repeating, right? That's the thing that you repeat to make the crystal. Okay. Yeah, and you know, and you can easily get this stuff. So if I just go up here and say lattice parameter iron, right? Well, there's this thing called periodictable.com, which I sometimes use, which tells you basically all the lattice parameters. So I could go to iron. Here's iron. Lattice constants. Okay, lattice constants. So they say 286.65 picometers. All right, fine. So they don't use angstroms here. They use picometers. Picometers are 10 to the minus 12 meters, right? So there are 100 picometers in 1 angstrom. That's why you know, instead of 2.87, you get 286.6, right? But you can see that if you just divide it by 100 and round it up, then you'll get 2.87. All right. So this is one way to get the lattice parameter. Of course, you know, you can go to anything else. Like if I click nickel here, I'll get something else, right? 352.4. Okay, so there's your lattice parameter for nickel. And then all the other ones, you can do the same thing. So this stuff is all fairly easily accessible. All right, so let's go to the remote session so that we can actually view this. So what I'm going to do, I'm going to log in, and remember that to log in, I have to begin by connecting with VPN. So let me do that. Okay, you should also remember to connect with your VPN. Oops. right, and then you're gonna get pinged on your phone properly. All right, so now I'm gonna go to the portal, portal.ada-ada, okay. And the first thing that I'm gonna do is I'm just gonna go to Files, Scratch, remember we're using the Scratch directory. And I'm going to upload, I'm gonna go to Intro LAMMPS, I'm gonna go to Visualizations, I'll go to Exercises since this is relating to one of the exercises, and I'm going to upload the file that I just made. So let's see. BCC structure, okay, that's the file that I just made, okay, choose. All right, there it goes. Now I'm gonna go back to my dashboard and I am going to go to Interactive Apps and I'm going to start my VNC session, all right. You have some stuff to select, then you press launch. So this is all the same as what we did yesterday. Now I just wait for a few seconds until that little thing pops up here. There it is. All right, here I am. Okay, so it dumps me into my home directory. So when I do ls, I don't see anything that I uploaded. And I don't know if this is related, Nadia, to the problem that you were having, but it's important to remember that when you log in, this takes you to your home directory, not to your Scratch directory. So the first thing to do is just say $Scratch. And this takes you to your Scratch directory. When I do ls here, now I can see my intro LAMMPS folder. Okay, so cd intro LAMMPS. Okay, I put it into this one visualizations thing, exercises. Okay, there it is. There's my thing. Right, you see, this is what I just uploaded. That guy. This is written in the CFG format. So basically the format that we were using last time for Atomi, but right now the extension is .txt. So I'm just going to change it so that Atomi doesn't get confused. So I'm going to use the mv command, which basically renames files. I'm going to rename this from bccstr.txt to bccstr.cfg, right? So all I'm doing is I'm changing the extension, okay? And then of course, if I want to use Atomi, I have to do ml atomi 3. Okay, and now I should be able to see it. Let's have a look. Ta-da! All right, there's my alpha iron. Oops, let me reduce the atom size here. You see, I've got a nice BCC structure. You see those atoms at the centers of the unit cells? If I rotate this around, you can see those center atoms are there, right? Here's my 110 perspective. Here's the 100 perspective, and here's the 111 perspective. Okay. All right. So this was almost everything that you had to do here was almost exactly the same as what you had to do with the simple cubic case, right? So it is almost exactly the same. The only difference is that you had to recognize that every cubic unit cell of the BCC structure has 2 atoms, right? So on the interior of this loop, you know, every time the loop goes over all the unit cells, you don't add just 1 atom, you add 2 atoms. So I think you guys already told me that an FCC structure has 4 atoms. So if I want to do the same thing with an FCC structure, what do I got to do? Anybody? What do I got to do if I'm going to use this approach to build an FCC structure? There's only one thing I got to do differently. Add 4 atoms every time the loop iterates. That's it, right? And you know, when you do that, you know, you're going to be displacing the atoms not from the corner to the center, but you're going to be displacing the atoms from the corner to one of the 3 faces, right? So, you know, I would have basically 1 atom that displaces to the XY face, so that would look like this. And then I would have another atom that displaces to one of the other faces, so it would look like that. And then I would have another atom that displaces to another face. So I would have basically this, right? And the only other thing that I have to do here is change this 2 to a 4, because now I have 4 atoms per unit cube. And you know, if I'm doing this, I think I was doing it for copper, right? So let's just look at what's my lattice parameter copper. Wait, not lattice parameter, atomic mass. I actually know the lattice parameter of copper by heart. It's 3.615 angstroms, 63.5, but I do not know the atomic mass by heart. So, wait, what did I say? 63.5. And I'll just change this to FCC, making FCC crystal structure, right? Voila, I'm done. Now I've got an FCC crystal structure. Easy peasy, right? Questions before we move on? What about the adding of a vacancy or the creation of a free surface? Any questions about that? Questions or concerns about that? So again, you know, I really encourage you to ask me questions now. You know, of course, you can always email me later as well. You know, you can also talk to your advisors. You know, your advisors will be able to answer these questions easily also. You know, I think that, you know, if you talk to anybody who's experienced in using LAMMPS, they'll tell you, you know, why are you spending time, you know, learning how to build these crystal structures in MATLAB? After all, LAMMPS has a command that will build crystal structures for you. Yes, it does. It's true, right? So this has already been automated in LAMMPS. But I think that, you know, I like to go over this as a way of introduction because it helps you to understand what one of these crystal structures really is, right? What it is, or, you know, basically any of these atomic structures. What it really is just a bunch of atom coordinates, okay? And you just, you know, all you have to do is figure out how to put those, you know, coordinates in the right place, and you can build atomic models, right? That's all it is, right? Building atomic models is all about putting atoms in the right place in a file. That's it, right? So, and after that, once you've put them in, then you can use LAMMPS to do things like calculate the energies and calculate the forces and things like that, right? So this is a fairly straightforward way to do some interesting science. You make a model, calculate energies or forces using LAMMPS. There's a lot you can do just with that, all right? Okay, so if there are no other questions, I'm gonna move on to the next part, which is, you know, actually running LAMMPS. So I'm gonna move to part number 2, which is energies. And there was this tutorial that came with that. Did you guys have a chance to look over this at all? Did anybody have a chance to read over at least the first 2 pages of this tutorial? Anybody? Yep, good. So this should give you at least a little bit of an idea, right? So, you know, I think that the important thing here is that if you specify all the positions of all the nuclei, and you're solving Schrodinger's equation, right? So basically, you know, let's say time-independent Schrodinger's equation, then you're basically assuming that the electrons are going to fall into some time-independent state, okay? And let's suppose that we only look at the ground state. What does Schrodinger's equation give you? It gives you an energy, right? So for any given configuration of atomic nuclei, you will get an energy for that configuration, right? So that's the way you should really think of a structure of atoms. It's basically a collection of positions, and Schrodinger's equation, or, you know, you can think of it as just physics, right? Physics gives you an energy for those positions. When you have those positions, physics will give you an energy. Now, of course, you can compute that energy using Schrodinger's equation, but solving Schrodinger's equation takes a lot of computing power. You have to run a big computer for a long time, It takes a lot of resources. And what that means is that if you actually want to do these kinds of calculations, you're limited in the size of the model that you can simulate, and you're limited in the number of times that you can evaluate that energy, just because it takes so long and it takes so much computing resources. So to speed up the process, what people have done is they've developed something that's known as interatomic potentials, right? And potentials are really nothing more than functions, right? So whereas Schrodinger's equation would take the positions of the atoms and then solve this big equation to give you an energy, right? Solve this partial differential equation known as the Schrodinger's equation. An interatomic potential will take those same positions and simply spit out a number, right? So you should view this as just a numerical function and not as a partial differential equation, right? So this is what I mean by potential function. Do you guys recall ever having worked with a potential function? And I guarantee that all of you have, right? You've all gone through freshman physics. So you've all, talked about Newton's law of gravitation, right? So you know that Newton's law of gravitation can be derived from a gravitational potential, right? Basically just the potential energy of two particles that are gravitating, right? That are interacting with each other via gravity. And you can write down an equation to express that potential. So the idea here with these interatomic potentials that we're going to use in LAMMPS is very similar, right? Very similar to a gravitational potential. We're just going to write down an equation that tells us the potential energy of a collection of atoms based on their positions. And of course, the potential functions that we're going to use to describe interactions between atoms are going to be much more complex, right? They're not going to be quite as simple as the gravitational potential, right? The gravitational potential is just 1 over r. The atomic potentials that we're going to be working with are going to be a little bit more complex. Their shape, their form, the way that they're written is going to be a little bit more complicated, but the idea is still the same. The idea is that you get a number for a given set of atomic positions. All right. Now, the other thing that you might remember from your work on Newton's law of gravitation is that if you have the potential and you want to derive the gravitational force, all you have to do is take the derivative of the potential with respect to the position of one of the particles and put a minus sign in front of it, right? So if you want to find the force on one of the atoms based on the potential, then you take the derivative of the potential with respect to the position of that atom, and you take the negative value of that, right? So that gives you the force. So in other words, if you have the potential, you can easily compute the potential energy, and from the potential energy, you can easily compute the force. And if you have the force, now you can solve F equals ma, right? F equals ma tells you how the atom is going to move, right? Again, Newton's laws. So you have the potential, you have the force, you can figure out the atomic trajectories in time, okay? That's a sort of very brief, very, very quick, generic idea of how these atomistic simulations run. This is basically how they run. All right. Now, implementing a code that actually computes the potential, that computes the derivatives of the potential, that uses those derivatives to get the forces, and then uses those forces to solve for the trajectories of atoms. It's actually not so difficult to write a code like that. I think that with any kind of programming experience, for example, if you've programmed in Python or if you've programmed in MATLAB, you've used any kind of programming language, it would probably take you a few weeks, at most a few months, to write a rudimentary code that runs atomistic simulations, right? So it's not that difficult. However, a few weeks or a few months is all that you have during the summer, and so you're not going to be writing your own code this summer. We're going to be using a packaged code, one that's already available, and that's LAMMPS, right? So if I go to LAMMPS, lamps.sandia.gov, LAMMPS is this is the website for LAMMPS. It's a code which is free. It's maintained by Sandia National Labs. It's very well documented. It's extremely popular, right? People use it a lot. You know, here you can see all the different journal covers that, you know, have been published based on simulations using LAMMPS. It's also very highly optimized, right? So if you write your own code, it might run, it might be correct, but it might not run very fast, or it might not allow you to run very large simulations, you know, basically because, you know, doing those things well takes just a lot of kind of technical polishing of the code, you know, computer science type things, not necessarily physics things, just sort of, you know, technical computer science things. And LAMMPS, the developers of LAMMPS have generated a lot of, devoted a lot of effort into optimizing LAMMPS. So LAMMPS is highly optimized. So that's another advantage for using LAMMPS. They have this nice little thing that if you hover over it, it's gonna like do a little simulation. So anyway, it's also very well documented, as I mentioned. So you can, for example, go to the manual. Right? If you click this, it'll show you a manual, it'll walk you through all the different things that LAMMPS does. One of the most useful parts of this, I think, is the commands link. Right? So if you go here, it'll list for you all the commands that LAMMPS can have. Right? And I'm going to tell you about some of these things as well. So, you know, no worries. You know, right now I just wanted to sort of give you a little bit of an overview. One other thing, you know, so over here you can see I mentioned that LAMMPS is free, right? So it's a community code. Nobody has to pay for it. You don't have to license it. Anybody can use it. It's free. If you go here, you can see you can download it, right? So there are many different ways to download and install LAMMPS. So it's not extremely difficult, right? It's actually not too difficult to download LAMMPS and install it on your own computer. I have never done this with a Windows computer, but I have done it multiple times with Macs. And those of you who have a Mac may or may not know this, but your Mac is actually a Linux box. It runs on Linux, right? So that's one of the reasons why when you go to your utilities folder, you have a terminal built in, right? Because your Mac is actually a Linux box. And so you can download all of these Linux files, you know, that MATLAB comes in, and you can put on free compilers on your computer, and you can basically run those compilers and build MATLAB on your computer and run it directly on your computer, right? And I think it's very, very convenient, right? I mean, because LAMMPS is actually a code that doesn't really require you to have a supercomputer, right? If you have a supercomputer like HPRC, then you can run enormous LAMMPS models, right? You can run LAMMPS models that have millions or hundreds of millions of atoms using a supercomputer. But if all you want to do is run models that have a few hundred or a few thousand atoms, you can easily do that on your laptop, right? So LAMMPS is a great way to, you know, to be productive on your laptop. It's the learning curve is not too steep, right? You know, with a little bit of playing around and a little bit of, you know, help towards the beginning, I believe that any of you can pick up LAMMPS. And if you're willing to make the investment to somehow install it on your computer, that's going to be even easier, because now anytime you go somewhere, you can just run LAMMPS on your computer and, you know, potentially do some good science. So I'm gonna turn that off. All right. So here I am back again in my virtual environment for HPRC. I'm going to turn off this animation or that visualization. So it's gone. Goodbye. I'm going to go down. Oh, by the way, I forgot to run this in Firefox. But the good thing is that if you type reset, which is what I did right now, even though you didn't see it, you type reset, it resets your X term, and now you can see my script again, right? So I just typed reset, even though you couldn't see it, it was there, and I pressed return, and it basically resets it so that I can actually see everything. All right. Maybe next time I'll actually remember to open Firefox instead of Safari. But anyway, so much for the last tutorial. I'm going to go to number 2. And I already went over the point defect crash course last time, so now I'm just going to go directly into the LAMMPS files, okay? And if I go to LAMMPS files, I'm in this folder now, I have these 4 files. Was everybody able to navigate to this folder? I'm going to give you just a second to navigate to this folder if you haven't had a chance to do that already. So let me know if you are having trouble getting there. Or if you're already there, then just ping me here on chat and say I'm there. While you guys are navigating, I'm just going to open this link here from Lisa that shows LAMMPS movies. Why not? Let's see some LAMMPS movies. Fiber dynamics. So these look like some kind of polymers, maybe. It's taking a while. Okay, I've got one person telling me that they made it. Anybody else made it? Yep. I'm just going to take it. I'm just going to take another few seconds, but I hope that the rest of you who are not replying here in chat are nevertheless able to follow along, because if you can't navigate to here, then you're not going to be able to do any of the little exercise thingies that I have planned. So, and if you have difficulty, that is perfectly okay. We're here to help you with that. So please do ask. We will help you to do this, right? We fully understand that doing command line stuff is not necessarily standard practice these days. So so if you have difficulty, by all means, let us know, and we can retrace our steps again if you want. Okay. Nobody's saying anything, so I'm just going to proceed. All right. So I'm just going to tell you a little bit about these files that you see in here. These files are basically the bare minimum files that you need to run a LAMMPS calculation. And actually, this is one more than the bare minimum. The bare minimum are just these 3 files. Right? These 3 files by themselves are the bare minimum that you need to run a LAMMPS calculation. The first one, I'm just going to move this over a little bit. There we go. The first one, this one, called cu_mission1.eam.alloy, is a file that contains the potential energy surface, right? That interatomic potential that I was telling you about just a moment ago. It turns out that it's easy to specify those potentials in the form of just written tabulated files. So I'm just going to show you what it looks like. You remember this more function that I had? It shows you basically what's inside the file. Right, so I did more, and what you see here is a header with a few comments, right? So this tells you this is a LAMMPS potential file written in a particular format. This particular format, I'm sorry, just one moment. This particular format is called the Dynamo 86 setfl format. Okay, so this is it's just a format. You don't have to worry about it. This potential is described in a paper. That paper was written by a researcher whose last name is Mission. His name is Yuri Mission. He works in one of the schools up in DC. I forget which one, but he basically works in that area. It's a mission potential for copper. Okay, it is a EAM potential. EAM means embedded atom method. It's a type potential. Okay. And this thing right here is basically telling you the paper in which you can read more about that potential. Okay, so PRB means Physical Review B. It was published in 2001, volume 63, and 224106 is the ID of the paper. Right. So if I wanted to look up that paper, I could type in this stuff into Google and it would pull it right up. But I could also just say, for example, because this is a very well-known potential, I could say mission copper. So it's probably going to pick it right up. Shin, copper, there we go. This is that potential in a NIST repository. This is the paper, I believe, that we'll see in just a second. Yep, here's the paper. If you're logged into VPN, then you automatically have access to this paper through the A&M libraries. So you should be able to just click it. And here it is, right? We evaluate the ability of an embedded atom method potential, as well as a different method called the tight binding method, which, never mind what that is. But anyway, here's your emission. He's at George Mason University in Fairfax, Virginia. All right, School of Computational Science. And if you're interested in exactly how this potential was built, you read this paper. Right? And it'll tell you everything about how they built this potential. Now, something showing up here in the chat. What is the difference between /scratch and $scratch? Okay, /scratch is a shortcut, basically, right? It's basically a shortcut that was built into the environment in LAMMPS so that you don't have to write everything from the very beginning, right? But you can just write /scratch/user/your .NET-ID/intro lamps, et cetera, et cetera. $capital Scratch is basically just a shortcut. It's like an acronym, if you will, for /scratch/user/your .NET-ID. Okay? Hopefully that helped. All right, so let me go back here to this thing. Finally, it says here that it's implemented by G. Ziegenhain 2007, and it tells you the contact information for the researcher that implemented this particular potential into this file, right? So, and then the rest of it, this thing means, this little pound sign means comment, right? So LAMMPS actually doesn't read any of this when it reads the file, it skips it, it's a comment. And all the stuff beneath that, so all of these things beneath, right, starting from 1 copper, all of this going down, is data, right? That's the data that actually tells LAMMPS, what are the properties of this potential. And if I, keep pressing more, I'll scroll through more and more and more of this data, and you can see that, down here, the percent sign is the percent, of the file that I'm going through is moving quite slowly. So you can see that this is actually a pretty big file. Right, this file is much bigger than the one that we were using before for the atomic structure. Okay, so you don't have to do anything more than this. I'm telling you this stuff just basically for background. And if you are interested in looking at other potentials, LAMMPS has a lot of potentials that you can use, right? So it has potentials for lots of different things. Let me actually see if I have them here on my computer by any chance. It's possible that I have them, but maybe I don't. Let's see. I don't. Maybe the LAMMPS. Let's see, potentials. No. I'm sure that somewhere over here you can find the LAMMPS potentials. All right, never mind. I'll show you something else. I developed some of my own potentials, right? So, for example, I developed a potential for copper niobium, right? This is a potential that a lot of people use. It's one of my claims to fame. So basically, this potential takes a potential for copper and a potential for niobium, and it joins them together to do the copper niobium system. So you can see it also has this header file. It's a 2-element potential, so it's got more stuff in it, and it's got data, right? And there are repositories for these potentials. You can download them, and then if you wanted to, model something else like nickel, you would need to get a nickel potential. If you wanted to model iron carbon, you would need to find an iron carbon potential, etc. Right? But the good news is that a lot of these potentials have been developed, so you will almost certainly not have to develop that potential yourself. Right? You'll be able to just download a potential that somebody else has developed. All right. So let's go back here. All right. Next, I'm going to show. I'm going to be just doing a very simple calculation here, basically that just computes the energy of a structure. Right, basically computes the value of the potential energy of a crystal structure. So to do that, I'm going to use a script, a LAMMPS script. And that LAMMPS script is, in this case, is going to be called in.lamps_energy, right? Over here is another LAMMPS script, which I called in.lamps_minimize. And that's a script that is going to not just compute energies, but also relax the positions of atoms. I'll come to that later. So for now, I just wanted to focus on this in.lamps_energy. All right, so I'm going to show you what's inside that. Okay, this is what's inside that file. So any of you can look at it. Basically, it says this is an energy calculation for a structure containing copper atoms. All right. It has a couple of different, commands here, and it's got, occasionally it has these pound signs, which basically mean that you're looking at a comment, right? So this one is basically saying what this script does. It has a few commands at the beginning. First, it's got the units command, then the boundary command, then the atom style command. These are standard commands that you have to issue at the beginning of any LAMMPS script, right? So the units are called metal, and it basically means that I'm tracking my distances in angstroms and my energies in electron volts, and my let's see, my masses are tracked in terms of atomic mass numbers, right? If you want to know what any of these commands mean, you just go to the LAMMPS website, you go to commands, you find the units commands, there it is, you press it, it takes you there, right? And it tells you what are the possible units commands, right? So these are examples, units metal, units LJ, there are different possibilities here, all right? And then if you scroll down, it'll tell you more, right? So units LJ tells you what is the definition for LJ type units. LJ basically, by the way, stands for Leonard-Jones. It's a very simple potential that a lot of people use when they start learning how to build these kinds of codes. Then there's another one called real. That's not the one we're using. We're using one called metal, and you can see, it basically tells you what are the units of what are the units that you use when you use the metal units, right? Mass is grams per mole, right? That's how atomic numbers are defined, right? So 63 for copper means that there's 63 grams of copper per mole. Distance, angstroms, time, picoseconds, energy, electron volts, velocities, forces, torques, everything. It basically tells you everything, right? And then there are a couple of other unit conventions that you can choose, okay? If you end up using different unit conventions, you can change these. A lot of times you don't have a choice. A lot of times you have to use whatever units are assumed by your potential. And as it turns out, most potentials for metals, which are, a lot of them are EAM potentials, use these metal units. So that's why I have that particular unit. Then there's boundary, right? Boundary basically tells you what are the boundary conditions. And you remember I told you every model has boundary conditions, and the atomistic models that we're using have periodic boundary conditions. So this PPP is basically saying that the boundaries are periodic in all three directions, right? So P in the X direction, P in the Y direction, P in the Z direction. All three directions is P. LAMMPS reads that as all the boundary conditions are periodic, right? So the Pac-Man boundary conditions. Finally, atom style, atomic, again, just another example of a sort of command that you have to issue at the beginning. You want to know exactly what it does? You guessed it. You go up here and you look at atom, sorry, not angle, it's atom style, right? Atom style, there it is. Okay, and you can read all about what the atom style command does. Okay? So these are just basically some simple setup commands. All right. Next command, read atomic structure. Right. So there's a command here that's called read data, and then there's this thing here, which basically tells LAMMPS the name of a structure file. Right. This is a structure file that I want LAMMPS to read. And if I go back to my directory, I'm going to do ls again. You'll see that I have a structure file here with exactly that name, copper subscript structure.data, right? So what this command says is LAMMPS, go off and read this file, right? And that's going to be your structure. And I'll talk more about the structure file in just a minute. All right. The next set of commands basically tells LAMMPS to read the mission copper potential, which I just told you about. So pair style is basically telling LAMMPS what kind of potential format this is using. Okay. And the particular type of potential format that I'm using here is EAM/alloy. Right. Chances are, if you're doing, work on LAMMPS during the summer, you're going to be working on one particular material using one particular potential. Your supervisor, your mentor, will help you figure out what that potential is. You will basically write in the type of potential and the name of that potential into your LAMMPS script one time, the first time you run it, and you'll never change it again for the entire summer. So, work with your mentor or your advisor, to make sure that you have the potential that you need, that you implement it into LAMMPS properly using these commands, and that's it, you're done. Okay, so pair style here says I'm using EAM alloy. Pair coefficient basically says that the interaction between any two atoms, these two asterisks say any two atoms, are being described by this potential file, and the atom types that they're describing are copper. Okay. Why this particular syntax? How do I know that these stars mean all atoms? How do I know to put the file name here? How do I know to put copper here? Well, you guessed it. I go back to my thing here for the LAMMPS commands. I look up pair coefficient. Right, there it is. And it explains to me exactly what everything means. Right, so pair coefficient, I, J are the atom types, and then arguments of certain types. If you scroll down, it will tell you exactly what arguments you can use. All right, so these are very, very simple sort of things that you can implement once with your advisor's help, and you'll be done. All right. Next, there's a comment here called log output parameters, and it's basically it has this command called thermostyle, and it basically just tells LAMMPS what you would like LAMMPS to output, right? So again, you can go back to the documentation and see exactly what is the format for thermostyle, but I'll just tell you, I am using not a standard style, not a standard output format, but a custom output format, okay? I want LAMMPS to output the things that I want it to output, okay? And not, whatever the standard is. So I have this custom thing. And then after custom, I tell LAMMPS everything that I want it to tell me, all the numbers that I want it to output. So I want it to output for me the step, and step in this particular case is not going to be super important because we're just going to take one step and we're going to basically just calculate an energy once and that's it. But if you're, for example, if you're running molecular dynamics simulations, then you're going to be calculating energies and forces over and over and over again because you're going to be incrementally changing the positions of the atoms. Each one of those incremental changes is a separate step. And I'd like to know how many steps the simulation took, okay? So this is not going to be super important yet, but it will be important later. Atoms means how many atoms. Now, in my simulation, the number of atoms is not going to be changing. But in some simulations, the number of atoms might be changing. If you're deleting atoms or putting atoms in, or maybe not all of your boundary conditions are periodic, so maybe atoms are leaving your system. So this basically tells me the number of atoms at any given time. Okay, temp is temperature, press is pressure, vol is volume, PE is potential energy, KE is kinetic energy, and E total is just the sum of the potential and the kinetic energy. All right, and that's it. Basically I'm telling LAMMPS to output all these things. And then finally, it has this last part, which says run 0. Run means run, right? It just means go do the calculation, okay? 0 means calculate energy and quit, right? So it's basically, if I had put something larger than 0, then LAMMPS would try to animate the atoms, would try to move them in response to the forces, but I don't want it to move the atoms. I want it to just keep the atoms where they are, calculate the energy, and quit, okay? So you can see that, all of this up to here is setup, right? I'm just setting things up, and the actual simulation is just this last line, right? So the LAMMPS simulation is very easy to run, and all this stuff up here is just setup. Okay, so let me go back here. The last thing that I have to tell you about is this structure.data file. Okay, so I'm just going to show you what that looks like. Okay, it is a data file. It has a couple of entries here. This, of course, means comment. So, so LAMMPS doesn't read this part. Okay. Next line, it says it's got 4,000 atoms. It's got one atom type. The atom mass is 63.5. It's copper. This is a way of specifying the dimensions of the unit cell. So basically, it's saying that the unit cell extends from 0 to 36.1 in the x direction, 0 to 36.1 in the y direction, same in the z direction. So it's basically a cube, right? And then after that, you've got all the atoms. So this thing is telling you the atom number. All the atoms are labeled. They're numbered 1, 2, 3, 4, 5, 6, 7, 8, etc. The next line after that, it says the atom type, right? And the atoms are all going to be of type 1, which in this case is copper. So the masses here say that type 1 atoms have a mass of 63.5, so they're all copper atoms. And then after that, you basically just have atomic positions. So you can see that this input file, this data file, has a lot of the same elements as the atomi file that we talked about before, but the format is a little bit different, right? So it doesn't have velocities, and it doesn't have a character here to state the name of the atom that you're looking at. It just has an atom type specified by a number. The header is different too, right? So the header doesn't look exactly the same. But I think that, at this point you should recognize that the information that's being conveyed in this file format is the same as the information that's being conveyed in the atomi file format. Okay, so it's pretty much the same information. The only one difference that I would point out is that, in atomi, the atom positions are specified as fractional coordinates in a unit cube. In this LAMMPS structure file, the atom coordinates are being specified in angstroms, right? So not scaled to fit in a unit cube, but actually given in angstroms. And that's just a difference in convention, right? Atomi has this convention that it specifies everything in a unit cube. LAMMPS, input files have this convention that all the atom coordinates are specified in angstroms. It's just a convention, it's just a choice. So long as you're aware of that difference, you can easily generate these kinds of files as well as, the atomi files that we talked about before. Okay, so at this point, I've gone through all the files that I wanted to show you, and now I'm going to just run some simple LAMMPS, calculations. So I'm just going to pause for a second, see if there are any questions. Any questions at this point? Raise your hand if you would like to ask your question out loud, or you can type it into the group chat if you prefer. Anybody? No? Okay. All right. If there are no questions right now, that's fine. So we'll just proceed. Feel free to ask me anytime. All right. So let's run LAMMPS. Before I run LAMMPS, I have to tell HPRC, my virtual session, that I'm going to run LAMMPS. To do that, I have to issue this command. Right? There are many different versions of LAMMPS, and this is just one version of LAMMPS. This is a relatively new version, so we're going to use this one. Okay, so we just have to type this into the command line. So I'm going to go back here. I'm going to say ml lamps slash, it was 24 October. I'm going to autocomplete by pressing tab. Okay, it should autocomplete. 24 October. Yeah, there it is. It auto-completed. All right. So I didn't have to type all that myself. I just pressed tab and it auto-completed. And then I press return. It's going to take it a few seconds, but in a minute I should get a success on my terminal here. Okay, good. Everything worked. You guys ready? You're about to run your first LAMMPS calculation. Everybody with me? Might be good to take a short break after running LAMMPS. Good, we'll do that. Yeah, I'm getting hungry too. We'll just do a couple calculation with LAMMPS, and then we'll take a short break. Everybody with me so far? Give me some feedback, guys, because I don't know like what's going on your end. Have you followed along thus far? Are you able to do, these things? Yeah? Okay, very easy. All right, so here's what we got to do. LMP space dash in space in dot lamps energy, and I'm auto completing, right? LMP is the command for lamps. Dash in means that I'm going to specify the script that's going to run lamps. It's the input file, right? And then I just say the name of it, and then I run it, and that's it. There you go. You just ran lamps. Okay? All this stuff that showed up on your screen is the output from lamps. And yes, you can autocomplete all the file names. I'm going to do it again. All right, so LMP dash in, and I'm going to say in, and when I press tab, all I'm going to do is press tab now. It autocompletes as far as it can without, to the point where it reaches a point where there's some files that it doesn't know how to autocomplete. So if I keep pressing tab, it'll tell me which files start with in.lamps. In this particular folder, that's in.lamps underscore energy, in.lamps underscore minimize. I want to run the energy calculation, so I'm just going to press P. That disambiguates between those two files, and I'm going to press tab again and autocomplete. So I don't have to keep typing everything. Right? This is really convenient. If you haven't, already, so I think somebody towards the beginning said, "Oh, I'm not, I can't type that fast." Well, nobody can type that fast. None of us actually type out all these things. We just use autocomplete all the time, right? So that's why it looks fast when you're, whenever you look at those like movies with the hackers and they're doing all this like, text, they don't actually type that fast. They're just using autocomplete. Okay, so again, I'm just gonna run it again, all right? So there it goes. All right, I'll talk about this stuff in here in just a minute, but first I'm just gonna do ls, all right? So that's gonna show me what's inside the directory. And you'll notice that I have the same 4 files that I had before, plus one new one, right? There's this new file that just appeared in the directory, log.lamps. Log.lamps is a file that basically takes all the stuff that appeared here in your command prompt and writes it into a file, right? So if I say more log.lamps, it's going to show me exactly what lamps ran. So it basically repeats the input file. And if I scroll down, it basically shows me all the stuff that it dumped out to the screen when I ran lamps. So I can just scroll through all the way. It shows me everything that came up on the screen, and then finally it ends. Let me just look at what's inside this file. So as I said, it's the same as what came out on your screen a moment ago. I'm just going to look at this file a little bit. Then, there's stuff here that talks about, the setup, like how did it bin the atoms and things like that. Eventually, when you become, expert in lamps, you're probably going to care about this stuff, okay? A quick question Advika had here. If we're changing the number of atoms in the structure file, do we just change the number 4,000? Yes, but you have to make sure that you also change the actual rows with coordinates, right? So if you delete one of those coordinates, if you're changing it to 4,000 and you don't change the number of coordinates, you have to basically make sure that those are consistent. Okay, we'll create a vacancy in just a moment. So I'll just I'll come to that in a minute. You'll recognize this stuff here. You see these steps: atoms, temperature, pressure, volume, potential energy, kinetic energy, total energy. Those are all the things that I was telling you about that I wanted lamps to output, right? Those are the things that I requested lamps to output. And right beneath it, all these numbers are the actual values, okay? So they don't, unfortunately, they don't align, right? These things are a little bit misaligned. I'm not really sure why lamps does that, but they're misaligned. Anyway, step 0, atoms 4,000, temperature 0. There's no temperature, right? This is a static structure. None of the atoms have any velocities, so it's 0 temperature. Pressure 0.07. Okay, I don't remember off the top of my head what the pressure units are for this particular convention. I think they're bars, but this is a low pressure. This is an MPa level pressure. Okay, volume. So here's the volume. It's given in cubic angstroms. right? So I've got 47,238.69 cubic angstroms. Then I've got my potential energy, minus 14,160.87 electron volts, okay? Then I've got my, then I've got my kinetic energy, okay, and that scrolls back over here. My kinetic energy is 0. It's 0 because I haven't given the atoms any velocities, okay? 0 velocity, you know, kinetic energy is 1/2 mv squared, right? If all the v's, all the velocities are 0, I have 0 kinetic energy. And so the total energy, which is the sum of the potential and the kinetic energy, is just equal to the potential energy, all right? If you look a little bit further, it'll tell you things like, for example, how much time did this simulation take? And this simulation is so small, and it's such a simple calculation that it takes so little time that LAMMPS, it's beneath the noise for LAMMPS, right? LAMMPS thinks this simulation took 0 time because it was so fast, right? You know, if you were to run molecular dynamics, it would take a few seconds. But this, you know, single energy calculation is super fast, so it basically shows up as 0. You know, in reality, it probably took like a millisecond or something, right? Okay. So let me go back here. With this information right here, this guy, I can actually do something interesting already, right? This is my total potential energy. With this total potential energy, I can calculate the potential energy per atom of copper, right? How would I calculate the potential energy per atom of copper from this value? Well, all I have to do is I just take this value and I divide it by the number of atoms, 4,000, all right? So you can open up MATLAB and do that in your virtual session, or you can just use a calculator. I'm going to use my MATLAB session out here on my desktop just because it's faster. I'm going to do minus 14,160.873 and divide that by 4,000, okay? So here's my answer. I hope you can all see the answer. MATLAB is telling me that the potential energy per atom is minus 3.54 electron volts, okay? This is also known as the cohesive energy of copper, right? So that's how much energy is keeping this crystal together per atom. If I go back to my files that I gave you just a moment ago, just going to go back to my tutorial session here. You remember I had this point defects crash course, and I was telling you the vacancy data. And one of the things that I told you in this table is the cohesive energy for a number of different elements. Here's the cohesive energy of copper, 3.54. What did we get? We got minus 3.54, right? So we've got the right answer, but off by a minus sign. Why are we off by a minus sign? Well, that's because when people report cohesive energy, they're using a slightly different convention. They're not saying what is the energy at which, the energy level at which the copper is sitting. They're saying, how much energy do I have to provide to knock the copper atom out and, you know, basically make it a free standalone individual copper atom. So basically the amount of energy that you have to provide to rip out a copper atom is 3.54, okay? So it's a different convention, so therefore the sign is opposite, but you can see that we got the number right? This means that the potential is working properly, all right? So very simple calculation. Let me just do one more calculation, okay, before we break. So this is going to be very, very simple calculation that I'm going to do, and then we're going to take a break, all right? So I'm going to go to my file manager. Remember this file manager that I had here. I'm going to go down to my energies directory, the thing that we're working with now. I'm going to go to LAMMPS files, okay? And I'm going to open copper subscript structure.data. I'm going to open this, okay? I'm going to use this edit command. Okay, and I'm going to create a vacancy, all right? This is the question that Advika was asking just a moment ago. I'm going to make a vacancy. How do I make a vacancy? Well, I showed you last time. I just delete an atom, right? So I'm just going to take any atom. This is a perfect crystal under periodic boundaries, so all the atoms are equivalent. I'm going to delete one of those atoms. It doesn't matter which one. I'll just delete this first one, okay? And then I'm going to change the number of atoms to 3,999, right? Because I went down from 4,000 to by one atom, okay? Save. All right, and now I'm just gonna go back here and I'm gonna rerun my LAMMPS command, right? I'm just gonna rerun the same command. Bang, all right. Now, what do I get for energy now? Now for the energy, I get minus 14,156.024, okay? Is that the same as what I had before? No, this is what I had before, right? So you can see that removing one atom changed the energy of this system, right? So the energy of the model has changed because I took an atom out. How do I compute the vacancy formation energy? Well, clearly I'm going to be taking the difference between the energies of these two structures, right? The structure that's a perfect crystal and the structure that is the perfect crystal minus one atom, right? So here's what I'm going to do. I'm just going to take the final energy, which is the one that's given here by LAMMPS. That's after I take the atom out, right? So I'm just going to write that in here, minus 14,156.024. I'm going to subtract from it the initial energy. Okay, so there's the initial energy. I'm subtracting that away. Okay, and I get 4.849 electron volts. Okay, is that correct or not? Let's go have a look. Here's my vacancy data. Vacancy formation energy for copper is 1.28 electron volts, whereas I got 4.849. It's wrong. What went wrong? What's the discrepancy? Well, the discrepancy has to do with the way that has to do with the fact that I'm actually comparing apples to oranges. You see, this energy over here is for a model that has 3,999 atoms, whereas this energy here is for a model that contains 4,000 atoms. If I want to compare apples to apples, I have to compare the energy of a model with the same number of atoms, with the only difference being that one of them has a vacancy as well as those 4,000 atoms. So normally what we would do in physics is we would imagine, taking an atom out of the interior of a crystal and putting it on a step on a free surface. However, we're not going to build a model of a free surface. We don't have to build a model of a free surface to do that. All we have to recognize is that the energy of an atom on a step on a free surface like this is equal to the cohesive energy, right? So putting an atom on a step on a surface basically gives the system one cohesive energy. And so I can actually do this calculation simply by taking the energy of the model after I've taken out the atom. So that's this energy over here. I'm going to subtract away one cohesive energy. Okay, so here's my cohesive energy that I had before. I'm going to subtract that away. And now I'm going to subtract the initial energy of the perfect crystal with no vacancy, right? So very, very similar calculation to the one that I did before. The only difference is that I'm adding a cohesive energy of 3.54 to the final state, just so that I have the energy equivalent of 4,000 atoms rather than 3,999. And when I do that calculation, I get 1.31. Let's call it 1.31, okay? Let's go back here. The actual energy is 1.28, okay? So obviously we're a lot closer, right? Before we had 4.84 or 4.85. Now we've got 1.31. We're much closer. We're only a few hundredths of an electron volt off at this point, okay? But we're still off by a few hundredths of an electron volt, okay? Where does that difference come from? That difference comes from the fact that we've created the vacancy, but we haven't relaxed it yet, okay? So my next step is going to show you how to relax this structure, and I'll do that after the break. So I suggest let's take a break. I'm going to call it a 20-minute break. So we'll reconnect at 11:45, 20 minutes from now. This should give you enough time to stretch a little bit, get some water, perhaps grab something to eat. And then we'll come back and we'll do the last part of this tutorial where I tell you how to relax these structures, okay? So I'll see you in 20 minutes, 11:45 Central Time. Thank you very much. Okay, and we're back. So hopefully all of you have had a chance to relax a little bit, stretch your legs, maybe grab a bite, and now we're just going to continue with this section that we have here on LAMMPS, using LAMMPS. So I have kept my VPN connection active, so I'm still connected to VPN. And what I'm going to do is I'm just going to go back to my virtual portal. So all the stuff that you've already seen me do before. I can share my screen just so that you see what I'm doing. Okay. So I'm on the portal website right now. I'm going to go to Interactive Apps, VNC. I'm going to start this up the same way that I had before. Okay. There we go. All right. All right. As usual, I have to start out by switching to Scratch. So I'm just going to do that. And I'm going to go into this part about energies. I was previously in the LAMMPS files section, so there I am again. And when we left off just a minute ago, we had finished computing vacancy formation energy. So the way that I did that is I first took a single crystal, perfect single crystal of copper. I figured out its energy, divided it by the number of atoms. That gave me the cohesive energy per atom. Then I took one atom out, recomputed the energy. I took the difference between the initial and the final energy, and I corrected for the fact that the final energy was computed on a model that had 3,999 atoms, one atom less than the original model. So I made that correction. I have some chat here. Okay. And we saw that, when I made that correction, the agreement that I had, first of all, the agreement for the cohesive energy was basically perfect. And that's by design. The potential was developed to perfectly reproduce the cohesive energy of copper. The energy that I first computed for the vacancy was way off because I didn't account for that extra cohesive energy. But once I did, I was pretty close. I was within a few hundredths of an electron volt. Okay, very, very close. And so the only thing that's sort of different now is I want to relax the model so that I can get something that's even closer. Right. So let me begin just by telling you. First of all, maybe questions. Are there any questions? No, I always like to ask for questions because sometimes questions become apparent only after you've had a little bit of time to sort of mull something over. If a question comes up, please do not hesitate to stop me and ask me. You can ask to be unmuted by raising your hand. All right. So what am I going to be talking about here? I wanted to tell you a little bit about relaxing atomic positions. So I'm going to use this little thing to do a little schematic. Right. So here's my schematic of an atom, of a crystal made up of atoms. Okay. Right. I'm coming to you from a different room, but as you can see, there's no getting away from some of the noise that's going on here. So let's try and make this look a little nicer. Okay, here's a crystal, right? I am going to take an atom out and create a vacancy. Here's my vacancy. We took it when we just ran this calculation a moment ago, we simply took that vacancy out and left all the other atoms in place wherever they were to begin with. Okay, so we didn't allow those atoms to shift at all. Right? We didn't do any shifting of the atoms. However, in reality, if you were to look at a real vacancy, then what usually happens is these atoms that are at the corners, right, these guys that are right next to the vacancies here, here, and here, these neighbor atoms to the vacancy tend to displace inward a little bit, right? So typically they'll undergo slight inward displacement. So that atom will go in that direction. This atom will go slightly inward in this direction. You know, this atom will go slightly inward in, in this direction. This one will tend to go inward in this direction, right? So you can see that generally there's going to be just a slight inward relaxation of those atoms. Those atoms will have had one of their neighbors deleted. Those bonds that it used to have with these atoms are gone. So the forces on that atom are a little bit imbalanced. And so to restore that balance, those atoms are going to sort of collapse inward just a little bit. So, you know, these arrows are sort of giving you an approximate idea of what that looks like. But in reality, what that means is that this atom displaces inward a little bit. This atom displaces a little bit inward. This one goes inward, and this one also goes inward. So if you were to look in the vicinity of a vacancy, those atoms tend to sort of come in a little bit. That's called a relaxation, right? Relaxations are driven by the desire of the atoms in the system to lower their energy, right? So they, rather than staying in their initial locations, they want to displace just a little bit so that they can lower their energies. They're going to sort of move inward a little bit to do that. The way that that we model that there are many different ways to model that relaxation, but one of the simplest ways to model that relaxation in LAMMPS is basically to do an optimization problem, right? We're saying the atoms would like to be sitting in a potential energy minimum, in a region that has a minimum potential energy. They're starting out from a location that is not at a minimum energy, right? They're starting out at a location where the atoms are slightly displaced from where they would prefer to be, okay? But we can actually find the lowest energy, minimum energy locations for those atoms by using an optimization algorithm, right? Basically just by using an energy minimization algorithm. You guys, I think in your math or numerical methods, you've all had some experience of finding minima, right? So, in your calculus class, you probably have found minima of parabolas and other polynomials just by finding locations with zero derivatives, right? You may have had a numerical methods class where you use something like Newton's method, or maybe some like bisection method or something like that to find a minimum in a function, right? Those are just examples. There are many different algorithms that you can use to find energy minima or minima of any function, right? And a potential energy function is just another function, right? It's a function that has many degrees of freedom. So it's not just a function of one variable, it's a function of many variables. The variables that it's a function of are the positions of all the atoms, right? Those are all the variables. So if I have 4,000 atoms and each atom has 3 coordinates, that means that I have 12,000 variables in my potential energy function, right? But I'm going to run an optimization algorithm that basically allows those positions to change a little bit so that the system finds its lowest energy position. And that's all that we mean by relaxation, okay? So that's what I mean by relaxation, and that's what I'm going to do now. So I'm not going to save that. All right. Since we took a break, I logged off and I logged back on. So I'm going to have to do this ML function again for LAMMPS. So ML LAMMPS 24 of October autocomplete. Takes a little while to autocomplete, but should autocomplete shortly. Still faster than writing it out. All right. Bang, there it goes. All right. So last time I was telling you about this in.lamps_energy. Now we're going to use this other script, in.lamps_minimize. Okay, let's have a look inside. Oops, minimize. There it is. So the first part looks very similar to the energy calculation. So I'm just specifying the units, boundary, atom style. I'm reading in the atomic structure, right? So I'm going to read in the same atomic structure as I had before. I'm reading in the potential file for copper, okay? And after that, I have a few other things. I have this thermostyle command, okay? So that's the same as what I had before. But then I have a few other things, right? So now I'm going to be taking multiple steps. I have a few other commands that basically say, you know, do this output after every step, you know, and that's basically it, right? So I added a little bit more information on how to do the output, but that's it. After that, I have a couple more things. So, you know, just for reference, right? When I did the energy command, here's the, actually, let me just put in a few spaces there so you can see. When I did the energy command, I had this thing about defining the units. I had the thing about reading the structure. I had reading the potential. I had specifying the output, and then I just ran it, all right? With the minimize, I have a few extra things. So I have, as I said, this thing about the units, the thing about the structure, the thing about the potential, this thing about the way that I want the output to happen. And then I've got three other things, 1, 2, 3. Okay, this one is called a dump command. And this dump command is basically just telling telling lamps that periodically, specifically every 10 steps, I would like lamps to write out a snapshot of what the atomic structure looks like. Okay, so you can look into the lamps documentation to see exactly what this dump, what is the syntax of this dump command. But you know, just to tell you very briefly, this is saying do it every 10 steps, write out all of the atoms as opposed to a subset, right? So depending on what you want to actually look at, you could have lamps write all the atoms or a subset of the atoms. I would like it to write it in CFG format. You may recall that the CFG format is precisely the format that atom I reads. And actually, I think I accidentally said something wrong. I'm actually, this 100 is actually the frequency of the output. So the frequency of the output is 100. So once every 100 steps. The 10 is just a label that says, that gives a name to this dump command, right? So this is dump command number 10. My apologies, I got that wrong. So the 10 is just a label. The 100 here is the frequency. So this is gonna output every 100 steps. It's also gonna output at the beginning and at the end, right? So it's gonna output the initial structure, the final structure, and then all the ones in between every 100 structures. I don't have it outputting every single time because, you know, the changes are going to be generally quite small going from one to the next. So I just do it every 100. This is the format for the name of the file that I want lamps to write. It's going to have the name copper_minimized. This asterisk here is the asterisk is basically a place where it puts the step number. So basically 0 is going to be the first step. And then, you know, 100, 200, 300, all the intermediate steps, and finally the final step, whatever that happens to be. The stuff that's going to come out is going to be the mass of the atom, the type of the atom, and X, Y, and Z coordinates. The S here is just a way of telling lamps that I want it to output it scaled so that it's sitting in a unit cube, which is what atom I reads. All right. And then this dump modify command is just a small modification that tells it to, you know, to write out, you know, individual files rather than all the files in one, rather than all the steps in one file. So never mind, this one's not terribly important. Okay, at the end, I have something that's called undump, and you see I say undump 10. So basically all I'm saying to lamps is, you remember previously I told you to output every 100 steps, and the command that I used to tell you that was this dump command, whose label is number 10. This command over here, the undump command, says, well, forget about that. command that I gave you back here, right? So I gave you this command up here. Now forget about it, all right? So this is not strictly necessary in this particular run that I'm doing here. It is something that I think you want to get into a habit of doing if you have longer scripts with multiple dump commands. You don't want to accidentally have dump commands going on when you're doing things where you don't necessarily want it to write out. This is going to be a burden for the memory on your machine if you're memory limited. So I put it in here just for, to show you good programming practice, basically. In between these two commands, in between this dump command and this undump command, I have this section here, which basically tells LAMMPS how I want it to relax the structure. I'm going to use an algorithm known as the Conjugate Gradient Relaxation method. It is one of many different optimization algorithms. It is built into LAMMPS, right? It's one of the most commonly used relaxation methods. So this first command here, min subscript style, is basically where I tell it to use the conjugate gradient method. That's CG, all right? And then this command right here, minimize, is kind of like the run command that I had before. You remember before I had run 0, basically meant run 0 molecular dynamic steps, just calculate the energy and output it, basically. So minimize is kind of the equivalent command that you would use for relaxation, right? So I'm saying minimize the energy of the structure. I already told the LAMMPS to use the conjugate gradient algorithm up here. And then over here, I have a few numbers that basically specify some parameters for the relaxation. These first two parameters have to do with the convergence of the relaxation. So in other words, when do I stop relaxing? Okay. I'm not going to talk about this in detail now. You can always look it up in the LAMMPS documentation if you like, or if you want, you can just use these same criteria in your future work. And then these last two numbers basically say how many iterations should this relaxation process go through before LAMMPS gives up, right? So you don't want LAMMPS going on and on and on and on trying to relax this forever if it happens to be stuck in a loop, right? You want it to eventually quit, right? No relaxation should ever take, whatever this is, 1 million relaxation steps. Most likely you will never do a relaxation that takes that many steps, right? In all likelihood, you will never have to do a relaxation that has more than a few hundred or a few thousand steps, depending on what exactly you're doing. Okay, so that's it, right? That's it. I'm going to come back here for just a second. I'm still going to use the same potential as before. My copper structure, I'm just going to show you that structure again. This copper structure still has the modification that I had before, right? So it still has 1 atom less than the perfect crystal. I've deleted that first atom over here. It's gone. Okay, so this structure has a vacancy in it. All right. So I can go ahead and use my LAMMPS minimize script to relax this structure. Actually, before I do that, what do you think would happen if I use my LAMMPS minimize script on a perfect crystal with no vacancy? Okay, just wild guesses. What do you guys think? Write it into the comment here, and I'll go and close the door to my bedroom. So. Okay, so the guess is that nothing is going to happen, and that's right. Nothing is going to happen. And why is nothing going to happen? Why do you think that nothing is going to happen when I run the relaxation command on a perfect crystal? What does the relaxation command do? It takes the positions of the atoms and moves them to the nearest potential energy minimum location. It's already at a minimum, precisely. Yeah, you guys got this, right? So you start out at a minimum, you run your minimization, nothing happens, all right? So I'm not going to run minimization on the perfect crystal because nothing's going to happen. I'm going to run minimization on the structure with a vacancy because something's going to happen. All right, so let's run it. All right, so here's how I do it. LMP. I want to chat this to you. I want to write it in here. So LMP dash in, and then in lamps minimize. Okay, that's it. And now I just run it. Off it goes. Okay, and now you see that things were a little bit more interesting than before. Before I just got one of these outputs, right? Only one row of numbers came out. And now I have a few more numbers, right? I have a few more rows. In fact, you know, and by the way, all of this stuff that you see here, you can also look into the log.lamps file, right? So I can just look into the log.lamps file. It's got the same stuff, right? All the stuff that came out on the screen has been recorded in the log.lamps file. So there it is. It's showing me the number of atoms. The number of atoms isn't changing. 3,999 always. It shows me the step number. And now, of course, I have step 0, and then I have step 1, 2, 3, 4. Altogether, I have 12 steps, okay? So this minimization process converges in 12 steps. Other things, pressure, volume, potential energy, kinetic energy. The kinetic energy, of course, continues to be 0 because I'm not giving it any velocity. But here now is the potential energy, right? And you can see the potential energy starts out at the value that we had before, right? So when I created the vacancy, this is the value that I had for the potential energy. Minus 14,156.024 electron volts. That's exactly what I start out with, right? So my atoms are initially at that position. That's where I start out. And then as I run the relaxation algorithm, this energy starts going down, right? Notice that the numbers here after the decimal point are getting larger, but there's a minus sign over here. So larger negative numbers means that the value is going down. It's becoming more negative, right? So 0.024, then I've got 0.051, 0.057, 59, 6, 1. You can see that as time, you know, as the number of steps goes on, this energy, this potential energy is decreasing by smaller and smaller increments. Right? So eventually it's not decreasing very fast at all. It actually, you know, when this output occurs, when LAMMPS writes this stuff out to the screen, into a file, it has a limited precision, right? So it doesn't write all the different digits that it tracks after the decimal point. So the energy could still be going down, you know, further at, you know, out at further digits behind the decimal point, but LAMMPS is just not outputting those. And eventually it reaches one of the convergence criteria that I gave it, and it stops. All right, that's it. Let's see, did it take time? No, it still took no time, right? So you can see that 12 relaxation steps for LAMMPS is still in the noise, right? So this is still something that takes like literally no time to compute. So LAMMPS is really, really fast. Let's do couple of things, right? So first of all, let's look at the energy at the end. Okay, so previously we were using the energy at the beginning to compute our vacancy formation energy. Now let's use this relaxed energy from the end of the relaxation process to recompute our vacancy formation energy. This guy right here. So I'm going to go back to MATLAB, and I'm going to bring back this this expression that I had, and I'm going to delete the energy that I had over here. This was the unrelaxed vacancy formation energy. I'm going to take that out, and I'm going to write in this new relaxed vacancy formation energy, which is minus 14,156.061. Okay, return. I have 1.2718. Okay, my vacancy formation energy is 1.2718. Let's look at what it is in the table that I reported. 1.28. Okay, 1.28 versus 1.272. All right, I'm off by less than 1/100th of an electron volt. Okay, that's pretty close. That's really good. Right, so that's I basically nailed it here. By the way, why do I not feel bad about ignoring that? You know, oops, excuse me, just one moment. Okay, pardon me. So why do I not feel bad about ignoring that fraction of 100th of an electron volt? Why do I consider that number to be a small number? You know, out of curiosity, does anybody have a feeling for why I consider that number to be small? I should probably look at my chat box here. Anybody's saying anything? Chat. Within margin of error, I mean, you mean that like I could set up my simulation a little bit differently, and I could, you know, and I could get answers that are a little bit different to within a few hundredths of an electron volt. That's probably true, right? That's definitely true. So for example, you know, if I look at this output that I have here, I see, for instance, that I have a pressure, minus 80. And that pressure keeps dropping, and it drops down to minus 103, okay? In whatever units LAMMPS is using here. So I'm not exactly at zero pressure, right? I could probably relax the volume of my simulation cell a little bit to adjust the pressure so that it's at zero pressure. And that might change the calculated energy by a small amount. Okay, so that's definitely one possible reason. Okay, so you know, I would say that that's you know, certainly plausible. Let's see, what else do we got here? Significant digits. Yeah, I mean, so significant digits would basically be saying, is another way of saying, you know, is another way about asking, you know, what's the margin of error? Like how many of these digits can I view as being sort of an accurate representation, as being sort of physically meaningful, let's say, as opposed to just, you know, some artifact of the way that I set this up. So that could be quantified by, you know, saying how many significant digits I have. The scale of the test is small as well, instead of moles of atoms, for example. True. The test of the scale of this test is definitely small. However, you know, a vacancy in a model that contains 4,000 atoms is basically has the same structure as it would have if you were to create it in a model that has, let's say, 100,000 atoms, right? So vacancy is such a localized defect that it really doesn't need a whole lot of atoms surrounding it to get things right. And actually, you guys all know that, you know, computers have limited precision, right? So whenever you do a floating point operation, you have a limited precision. And when you have more atoms, that limited precision is allocated to storing the energy of the entire system, right? Which is obviously much bigger because you have more atoms, okay? So you actually have fewer digits at the low end, right? And your number of significant digits actually decreases when you make the model size bigger, right? So bigger in atomistic simulations is not always better. But smaller is sometimes actually better. Due to accuracy of floating point numbers, not exactly. We have enough accuracy here. I think we're running this in 32-digit precision, so we should have enough accuracy. All right. The reason I'll just tell you, the reason why I'm ignoring it is because whenever you ignore something in physics, right? Whenever you say that something is negligible, it's always negligible by comparison to something else, right? In physics, we always say that things are negligible by comparing them to something else, right? So here I want to say that an energy difference less than 1/100th of an electron volt is negligible. And if I want to make that argument, I have to say that it's negligible by comparison to some other energy which is significant in this problem, right? And one significant energy, which is going to be, you know, of importance in any real problem that you work on, is the thermal energy. Now, of course, I haven't put in any thermal energy into this model. Thermal energy comes from atomic vibrations. And if all of my atoms have zero velocities, then they have no atomic vibrations. Okay, so I have no thermal energy in this model. However, if I, you know, in reality, if I were studying a real material, then I would have a certain amount of thermal energy. Does anybody know how much thermal energy there is per degree of freedom in an atomic system? So what's the degree of freedom? Degree of freedom is one of the sort of position variables of an atom, right? How many degrees of freedom does an atom have? It has 3. It has 3 position variables. How much energy is in each degree of freedom? How much thermal energy is in each degree of freedom at thermal equilibrium? Anybody? The thermal energy per degree of freedom is the temperature times Boltzmann's constant divided by 2, kBT. kBT divided by 2. That's the amount per degree of freedom. Okay, so in fact, Boltzmann's constant has units of energy per degree, per Kelvin, right? So electron volts per Kelvin. You know, temperature times Boltzmann's constant tells you the thermal energy, right? Any idea of what that energy is? What is kBT times T at room temperature, right? Room temperature is about 300 Kelvin. Anybody have any idea how much thermal energy there is at room temperature? Excuse me. Yeah, pretty close. 30 millielectron volts, or 3 hundredths of an electron volt, right? Another way that I like to say it is 1/40th of an electron volt. So that actually comes out to be about 0.025 eV. Okay, that's, you know, a good factor of 5 or 4 or 5 larger than that discrepancy that I saw, right? So the discrepancy between my calculated vacancy formation energy and the real vacancy formation energy is, you know, smaller than the thermal energy per, thermal energy that this atom is going to have. Right? This atom is going to have a larger thermal energy than that. So thermal energy is just kind of random jiggling noise. Another way of saying that is that difference is in the noise. It's in the thermal noise of the model at room temperature. Okay, so it wouldn't really affect the behavior of the vacancy because it's smaller than the thermal energy. Okay, so that's why I feel comfortable ignoring it. All right, let me go back to this calculation that I have here. All right, so I've looked at the outcome here. Next thing that I'm going to do is I'm going to look at what's in my directory. All right. And you can see that in addition to the 5 files that I had before, I have 2 additional files, copper_minimize0 and copper_minimize 12.cfg. Okay, you remember I was telling you that in this script I was telling LAMMPS to output the structure periodically. All right, so that's exactly what LAMMPS did, right? So it basically took the structure, it outputted it, I told it to output every 100 steps, but of course the whole minimization took only 12 steps. So really the only structures that it output are the initial and the final one. There were no intermediate structures to output here. And if I want to see them, I can just open them using Atomi. So let's do ML Atomi. Since I logged in recently, I'm gonna have to rerun this so that this knows to run Atomi. So ML Atomi, now I'm gonna do A3 copper minimized 12 CFG, right? There it is. All right, let's see if I can find that vacancy. It should be somewhere in there. Can I find that vacancy? I think I see it. There it is. Oops. Do you see it right there? Can I increase the size a little bit? You should probably see that there's an atom missing right there at the corner. Maybe if I shift this under periodic boundaries, it'll become a little bit easier to see. I'll increase the atom sizes a little bit still. See, there's that vacancy. Let's see, how can I, there we go. So I can zoom in a little bit. You might, inspecting this, looking at this, you're probably not going to be able to really see how much these neighboring atoms, this atom, this atom, this atom, this atom, you probably can't really tell how much those atoms displaced. They displaced so little, right? The displacement around a vacancy is so small, the amount by which the energy relaxes is so small that you can't really tell just by looking, right? You can calculate, you can definitely, record the positions of the atoms before and after and see how much they've displaced. It's just going to be such a small number that you can't really see it. right? You would have to, calculate that or somehow artificially magnify the displacement so that you can actually see it. But anyway, that's your relaxed vacancy. I think last time I was hoping to show you how to color the atoms according to their coordination number. I might be able to do that now. Let me see. What was the command that I used to color by coordination number? I'm just looking into the notes from 2 days ago. Okay. K. All right, so let's do K. No, it doesn't have the right nearest neighbor distance, so it doesn't really color it properly. Unfortunately, I don't know how to use all the keys on this virtual keyboard, so so I can't really. I'm not really sure how to make it happen. I know how to make it happen on my Linux box. But anyway, I think that vacancy is nevertheless quite easily visible. Okay, so I'm going to quit this. Okay, reset because it's got some issues. All right. And, this is a very simple calculation that you can do. And with this calculation, you can already work one of the exercises that I've assigned for you based on the stuff that we went over in this session. Okay, so in particular, if you can put in one vacancy into a model by taking out an atom, then you should be able to put in two vacancies, right? It should be very easy for you to calculate the energy of a system containing two vacancies. And if you can compute the energy of two vacancies, then you can compute that energy as a function of the distance between the vacancies. So I've assigned for you a very simple exercise for you to do, okay? Compute the vacancy binding energy as a function of the distance between two vacancies, right? So what you have to do for that is you can create for yourself a model with one vacancy in one location, another vacancy at a nearest neighbor location, compute the energy of that model, compare it to the energy of a model that has two well-separated vacancies, okay? And that'll give you the vacancy binding energy. Here I've plotted for you the binding energy as a function of distance between the vacancies. So you can see that when the distance between the vacancies gets large, the binding energy goes to 0, meaning the vacancies aren't bound at all. They're behaving as if they were just isolated vacancies. But if they're close together, if they're at a nearest neighbor, if they're at a nearest neighbor location, if they're right next to each other, then they bind to each other with an energy of about 0.14 electron volts. Right? So those of you who attended the seminar yesterday on radiation damage might remember that when vacancies come together, they can cluster. Well, why do they cluster? They cluster because when they get together, they bind, right? And that binding comes from the binding energy. With everything that I've told you about making models in LAMMPS and running relaxations with LAMMPS, you can compute this binding energy. You can compute the binding energy curve as a function of inter-vacancy distance. Okay? So try that out as a little exercise to see if you can do that. Any questions about that? Let's see, chat. How do you make the atoms larger? What I do is I use my function button and I press up or down, up arrow or down arrow, right? So I use my function atom up or down. That's on my laptop. I don't know how it's going to work on your laptop. I think that on a sort of standard QWERTY keyboard, you actually have to press the page up and page down button to make the atom sizes change. If you have difficulty making that happen in Atomi using the buttons that I'm telling you about, what I encourage you to do is go to that link for Atomi that I gave you in the first tutorial, and that link has a manual for Atomi, and it'll tell you precisely which buttons to press to make all those different things happen. And this is, by the way, true for Atomi, it's true for Oviedo, it's true for LAMMPS. This stuff that I'm telling you here is just a starting point, right? My hope is that you guys will take this, and this is going to be like an easy point for you to pick up and then go use the online documentation, maybe have some support from your mentor, your supervisor, and take the next step yourself. Okay. We can also do things like set up a separate channel on Slack, for all the LAMMPS users. We could make a OREU LAMMPS channel on Slack, and then everybody who's using LAMMPS can basically just communicate with each other and troubleshoot with each other all their LAMMPS issues. So we could definitely do that. Let's see, we've got some more questions here. A page up and page down changes the size of atoms. Yes, okay. That worked. If I wanted to make a substitutional point defect, would I go about it similar to a vacancy? What parameters would I have to change? Substitutional defects are very simple, right? They're even simpler than vacancies. How would I do a substitutional defect? Well, I don't know. I think, Nadia, you mentioned at some point that you're looking at iron chrome, is that right? So if you're doing iron chrome, then the first thing that you need is a potential, right? Right here, I have a potential that has just copper. You're gonna need a potential that has iron and chrome in it, okay? So I'm gonna show you that potential again. This is just the copper potential. You see, this has just one atom type. It has a 1 here and it has a copper, right? If I were to look at a potential that has 2 atom types, it would look a little bit different, right? So I'll just show you one of my potentials with 2 atoms. Here is a nickel aluminum potential. I'll just open that. And I know nickel aluminum is not what you're going to be using, but actually at Vika, that's what you're going to be using. So you can look at this. So anyway, you can see that this one has 2 atom types, right? It has 2. It has nickel and it's got aluminum, right? 2 atom types. Nickel is going to be called 1. The label of the atom type label for nickel is going to be 1. The atom type label for aluminum is going to be 2. Okay, so if I now go back here and look at my copper structure file, right? Here's my copper structure file. You see it's got just 1 atom type, 1, and it's got this mass, okay? And if I look at these rows here, I've got 2 as the index of the atom, that's just the name of the atom. And after that, I've got every single one of these rows is labeled as 1, okay? That means that every one of these single rows is an atom of type 1. And in this very simple example, there's only 1 type of atom, it's copper. Type 1 atoms are copper, right? If I had been using this potential and I had 2 types of atoms, then I could change this atom type from 1 to 2, right? So let's say atom type 1 is nickel, right? So if all the atoms are type 1, then that means all the atoms are nickel. And if I change one of these atom types from 1 to 2, then I'm changing it from nickel to aluminum, right? I don't have to change the position of the atom. I don't have to change the index of the atom. I don't have to change anything about the atom except the type, right? And all I have to do to change the type is to change this number 1 from a number 2. So when you're doing your iron chrome, all you're going to have to do, if you want to study a substitutional defect, all you have to do is change the atom type from number 1 to number 2, right? And if iron in your potential is atom type 1 and chrome is atom type 2, bang, that's it. Do you still have to relax the structure after that? You bet, right? Because whatever structure you started out with is going to be the relaxed structure, assuming that those atoms are whatever they were initially, iron, right? But if you change one of them to chrome, now the bonds between that chrome atom and all the neighboring atoms are going to be different than the bonds that were there before. And the positions of the atoms are going to have to adjust a little bit. So you'll have to relax, right? So the positions of the atoms will change. The energy of the atoms will change. So after you do that, after you change the atom type from 1 to 2, you'll also have to do the relaxation. Okay. Is it okay to launch a feedback poll with 2 or 3 questions? Yes, but I'm not done yet. So I wanted to do a couple more things before we're done, right? So I have time until 1 and I plan to use it. So I'm going to keep going until 1. Are there low doping concentration potentials? I gotta tell you, one of the nice things about potentials is it doesn't care what the concentration is. So you can do a low concentration, you can do a high concentration, you can do any concentration, right? That's one of the nice things about potentials. You can do any concentration you like, and it's just gonna, compute the number for you. Now, potentials, of course, are not Schrodinger's equations. So they're not like as accurate, right? They're not as fundamentally accurate as Schrodinger's equation. So some potentials might do better, like they might be more accurate in the dilute limit than in the concentrated limit. You can also have potentials that are more accurate in the concentrated limit than in the dilute limit. But my guess is that most of you are going to be working with relatively simple, well-known, well-developed potentials that are just accurate over the whole composition range. I think that's going to be the case. All right, Lisa has to sign off. So thank you very much, Lisa. Hopefully Braden has the poll that you want to run. Yes? Yes. Excellent. All right, so you guys are going to be polled after this is all over. Do we have any other questions here? No other questions right now. All right. I wanted to run another example for you, very simple example. So I'm going to go back to this interactive session. I'm going to go to my files, Scratch, Intro to LAMMPS, Energies, LAMMPS files. Okay, and I'm going to open this copper structure data file. Edit. All right. You remember how I told you in my little intro to point defects last time? Let me just actually use this. Oops, no, not that. Here we go, point defects crash course. All right. I mentioned to you that there are several different self-interstitial structures. Right, you remember these guys? I was telling you about all the different self-interstitials that you could have in an FCC material. Copper is FCC. And I mentioned to you that there are these dumbbell structures, right? And the dumbbell interstitial structures are where you take an atom out and you replace it with two atoms, right? So I already have a structure where I've taken an atom out. I've created a vacancy. Why don't I use that structure to create a self-interstitial atom? I'll just create the self-interstitial atom by putting two atoms, and I'm going to put them into this 100 split dumbbell configuration. The way that I built this model, all the 100 type Miller indices are aligned with the coordinate axes. So 100 is the x-axis, 010 is the y-axis, and 001 is the z-axis. All right. So if I want to make a 100 split dumbbell, I'm just going to put in two atoms that are aligned along the x-axis. Okay. So I'm going to make one of these models, and we'll just go through the process of relaxing it, just so you have a little bit more, experience doing this. And I think relaxing a self-interstitial atom model is a little bit more interesting because the relaxation energy is much larger, and the relaxed structure looks more interesting than the structure of a vacancy. It's sort of a more interesting structure to look at. Okay, so I'm going to put in an extra atom. All right, so I'm going to put it in at the location where I removed an atom to begin with. The atom that I removed it was sitting at the origin, 000, right? That's the atom that I removed. So I'm going to put an atom back, right? So let's put it back. I'm going to give that atom a name 1, right? The index that I'm going to give it is 1, the same index that it had before. It's going to be a type 1 atom, okay? I want to make a dumbbell configuration, so I don't necessarily want to put that atom at the origin, right? I want to put it a little bit offset from the origin along the x-axis so that I can make that dumbbell. So how much should I offset it along the x-axis? Well, I don't know. And frankly, I don't have to get it perfectly right because I'm going to run my relaxation algorithm after this anyway, and I'm going to let that atom find its happy place, okay? So all I have to do is make some kind of reasonable guess about where that atom is going to be. So when I look at the coordinates of the face center atoms, like this is a face center atom right here, I see that it's got the coordinate is 1.8 angstroms and then 1.8 angstroms. So I'm just going to guesstimate. I'm going to put in minus 0.8 angstroms along the x direction, 0 along the y direction, 0 along the z direction. Okay, so I've added one atom. And I want to add one more atom because I'm making a dumbbell. Okay, so I'm going to have to give this next atom an index. Okay, can I give it an index of 2? No, because this atom already has an index of 2, right? In fact, if you scroll down, you'll see that I've got indices from 1 to all the way up to 4,000 already taken, right? because I basically just assigned indices going, sequentially from 1 to 4,000 when I built this structure. So I'm just going to give this atom an index of, come on, scroll. Okay, I'm going to give it an index of 4001. Okay, that's the first unused index. And these indices don't have to be in order, right? So it's okay if they're out of order. So I'm just going to give it an index of 4001. It is also going to be a type 1 atom. It's going to be the second half of the dumbbell. So I'm just going to put it, offset from the origin along the x-axis by the same amount as I offset that first one, except in the opposite direction. So 0.8 rather than minus 0.8, okay? And then 0 and 0, all right. So I've added 2 atoms. So now, instead of having 3,999 atoms, I'm gonna have 4,001 atoms. Okay, that's it. Save. Let's go back here, okay. When I look at this structure file, all those changes that I made should be already in there. There it is, I have 4,001 atoms, all right. Let's run LAMMPS, LMP-in LAMMPS minimize. There it goes. All right, so as you can see, now this whole minimization took a little bit longer. There were, how many minimization steps? 25 minimization steps, okay? Minimization steps, there were 25 minimization steps. And it took a whopping 1 second for LAMMPS to do this. So you can see that LAMMPS is pretty fast at this. If you want to do things like create different interstitial structures, you can do that pretty fast. All right. When I look at the energy, let's look at the potential energy here, right? So the potential energy starts, oops, can't go all the way to the top. So let's just look at my log LAMMPS file. It's got all the same data. Here it is. Initially, my energy is this. That's my initial energy. Let me record it here in MATLAB, because I'd like to be able to figure out how much the energy dropped. So I'm going to say minus 14,153.056 electron volts. All right. And now I go all the way back to down to the bottom. This is the final energy. All right. So if I want to know how much the energy dropped, I take final minus initial. So I'm just going to write in the final energy here. Final energy is minus 14,161.336 minus the initial energy, which is this negative number. Okay. So as a result of this relaxation, my energy decreased by 8.28 electron volts. Is that a lot? Anybody have any opinions about whether 8.28 electron volts is a lot? Yes, that's a lot. That's a lot. That's much larger than the formation energy of a vacancy. It's even larger than the cohesive energy, right? So, and if you recall, if you remember, how much of a relaxation did we get when we relaxed the vacancy? Right? When we relaxed the vacancy, we only got a few hundredths of an EV relaxation, right? The perturbation that a vacancy makes in a crystal is much smaller than a perturbation that a self-interstitial makes in the crystal, right? So the relaxation that is needed to accommodate the interstitial is much, much larger than the relaxation that's needed to accommodate the vacancy. Let's calculate the formation energy of this interstitial, right? So the final energy is this one. That's the final energy, okay? And this is for a model that contains 4,001 atoms, right? So what we would really like to do is take this final energy that we have and subtract from it the energy of a perfect crystal that contains 4,001 atoms. What's the easiest way for us to do that? The easiest way for us to do that is just to subtract 4,001 times the cohesive energy per atom, right? Because we know that in a perfect crystal, every atom has an energy equal to the cohesive energy, right? It's a perfect crystal. We have the cohesive energy, it's right here. It's still in my MATLAB window, so I'm just gonna copy and paste it. Here's my final energy, this is my final energy. I'm going to subtract from that 4001 times the cohesive energy per atom. That's the energy of a perfect crystal with 4001 atoms. Okay, so I'm subtracting the energy of a perfect crystal from the energy of a defective crystal with the same number of atoms. That gives me the defect energy. That gives me the energy of that self-interstitial defect. All right. 3.0042 electron volts. How does that compare to the actual formation energy of a split dumbbell interstitial for copper? Okay, so in copper, the energy of a split dumbbell interstitial is 3.23 electron volts. Okay, so we are actually slightly underestimating the formation energy of a 100 split dumbbell in copper. The energy difference is a little bit bigger than what we had before. It's definitely bigger than the thermal energy. You know, unless you look at the thermal energy at like 3,000 Kelvin or something. So this is actually just a shortcoming of the potential, right? It turns out that the potential, this particular potential does not reproduce the formation energies of self-interstitial atoms to within that precision. It's frankly not terribly surprising because if you read the paper that describes this potential, it turns out that this potential actually was not fitted to reproduce the formation energies of self-interstitial defects. So the fact that it does as well as it does, and the fact that it predicts the right structure, the right lowest energy structure for the lowest energy split dumbbell, is a kind of success in its own right, but it doesn't nail the energy. So that's just a drawback of these potentials. You're not always going to get something that's perfectly accurate, you know, down to the quantitative scale, right? But we got that, right? So we can calculate the formation energy. Let's go back to this thing here. All right. So next we have I'm looking at these files, these structure files that were outputted. Right. This relaxation process took 25 steps. This file right here is the last step in that relaxation process. It's written out. I can look at it with Atomine. I can't remember if I already did. I think I did. All right, so let me just do A3, copper, minimized, 25. Okay, let's have a look. So let's look at this relaxed self-interstitial structure. Okay, I'm gonna reduce the size a little bit. I can already see the self-interstitial up here. You can kind of see it in the corner. I'm gonna shift this under periodic boundaries. This is a much more sort of visible defect, as you can see, than the vacancy, right? The vacancy was not like super visible. I had to sort of squint and look carefully to see it. This self-interstitial is kind of painfully obvious, right? It's very easy to see. I'm gonna shift my perspective a little bit. I rotated the view here by 90 degrees. Looking from this direction, I don't see it as well. Which direction do you think I'm looking along right here? Anybody have a guess which direction I'm looking along? Which crystallographic direction? Which Miller index direction am I looking at right now? Anybody got a guess? The 100 direction. Yes. Remember, this is a 100 dumbbell. It's aligned with the 100 direction. So you're basically looking along the axis of the dumbbell, which is why you can't see it. All right. But if I look in this direction, right, so I've rotated it. Right? So I'm basically using a key that rotates. So this is the direction that I was looking at just a moment ago, right? This is the direction in which I can't really see it very well. And if I rotate by 90 degrees to this direction, now I can see it very easily, right? Now I see that dumbbell right there. And let me zoom in a little bit. Okay, so this is zoomed in. Here's the dumbbell right here and right here. Those are the atoms of the dumbbell. And you can see how it's actually pushing the neighboring atoms out, right? So these neighboring atoms are significantly pushed out. The relaxation that this defect created is much larger than the relaxation that the vacancy created, right? You remember with the vacancy, we really couldn't even tell that the atoms had shifted. But in this case, it's very easy to see that the atoms had shifted, all right? So simple way to make self-interstitial structures, all right? So I'm gonna stop it here, okay? With this last bit that I did, you should be able to do the second exercise for this segment. So if I go to exercises, right, I told you about how you can use LAMMPS to compute the binding energy of two vacancies. The second exercise that I put in here is basically to say, go in to LAMMPS and create models of all those self-interstitial structures, right? So I told you that there are 6 different canonical self-interstitial structures in copper. With the stuff that I told you right now, you should be able to go on and just calculate all those self-interstitial structures, right? Just create them, relax them, find their formation energies. Here are the answers, by the way, right? So I'm giving you the answers for the mission potential. These are the formation energies of all those structures. I think that for this calculation, I used a smaller model, so the energies are a little bit different than the ones that I showed you here, because I used a 4,000 atom model here, whereas here it seems like I'm using a smaller model. So you know, you can see that I have all these different structures, the octahedral, tetrahedral crowd ion. The 1O split dumbbell has the lowest energy, so it's the thermodynamically stable self-interstitial structure, and all these other ones have higher energies. But you should be able to actually build those models, relax them, find the formation energies, and visualize them, look at them, right? So this is something that should be actually really easy for you now with everything that we've done. Okay, we're pretty much at the end of our session here. So I just wanted to, you know, wrap this up with just a very, very brief with a couple of very brief statements. First of all, I didn't get through this molecular dynamics part here. So we have a couple of options, right? I could schedule another session and go through the molecular dynamics part, right? I could do that. The alternative is you can just take this description here. It gives you a blow by blow, you know, step-by-step description of what you should do. It has all the LAMMPS files that you need right here, right? So I gave you some LAMMPS files to do, you know, melting of a crystal, you know, by raising the temperature. And things like that. So, so you can just try it yourself, okay? But if you want, you know, we can also set up another session, maybe next week, maybe the week after that, and just do this, this molecular dynamics segment as well. However, I would not want to, you know, jump directly into this molecular dynamics segment until you've all had a chance to work the exercises from today's tutorial and from last Tuesday's tutorial. Right, so I think that, you know, that should give you enough to do just to sort of get comfortable with how, you know, how to build some of these models and how to relax them, so that when we, you know, if we do end up doing the molecular dynamics segment, you'll be much more caught up and much more up to speed and much more comfortable with using the command prompt and navigating all these different visualization packages and running LAMMPS and things like that. In the meantime, please feel free to email me or contact me on Slack. I'm happy to try to answer questions. And again, if there is interest, we can set up a separate Slack channel that's basically just going to be a sort of user support group for LAMMPS. So if that's something that people are interested in, please let me know, and I'm happy to try to set that up as well. So Slack channel will be helpful. Okay, so we'll set up a Slack channel for LAMMPS, and to be honest, I don't know exactly how to do that. So I'm gonna have to ask somebody how to do that, and hopefully it's not going to be difficult to get people, you know, to get people joined into that channel. So I'm going to pause right now. Are there any questions? The last thing that we have, you know, before we sign off is that you're just going to get a very simple poll from the organizers of this tutorial. I'm just going to pause and see, does anybody have any questions about whatever we covered today, running LAMMPS, you know, getting on HPRC, visualizing, calculating formation energies, any of that? Do you guys have any questions? Any questions about the exercises? No questions? Okay. Well, in that case, we're just going to give it a few more, I guess, minutes for you guys to finish up answering this poll, and after that, I'll sign off. I'll hang around for a little while longer in case anybody has any questions. You guys can continue working on the poll, and I will, in the meantime, just hang out here and maybe try to see if I can work on that Slack channel.